Hello and welcome back to our data structures and algorithms series. In this video, we will explore the stack data structure. This is a fundamental data structure with various applications in computer science. We will delve into its properties, operations, and also the real-world uses of the stack data structure. By the end of this video, you will gain a solid understanding of how stacks function and their significance in algorithm design. Just like these plates here, a stack data structure, and actually this is also called a stack of plates. So a stack data structure also organizes the data in such a similar manner. So for example, in order for you to be able to access this, is it orange plate here, you have to begin by removing what is on the top. Then you go on to the next plate, you remove it, then this one, all the way down to the orange plate. So as we are going to see, a stack data structure can only be accessed from the top, going down. So what is a stack? So a stack is a linear data structure, meaning that in memory, the data is stored one after the other in contiguous memory locations. Or for you to be able to access the data, you have to move from one data segment to the next data segment. Now, what is important to remember is the fact that a stack data structure follows what is commonly referred to as the last in, first out principle, LIFO. So just like in this image, if we need to access the items here, we have to begin from the top block, then we come to this block, then to this block. So this is referred to as last in, last out, because last in, first out, or LIFO. So whatever was placed as the last one is the first one to actually go out, is the first one to go out. Then we also add and remove elements from the top. So we cannot remove anything that is not on the top. We cannot, for example, remove this or remove this before we remove what is on the top. And finally, just like the stack of plates we saw in the previous pictures, we always remove and add things from the top. So just as a reminder, where does the stack lie in this particular tree of different data structures? So indeed, you can see that it's a non-primitive or abstract data type. It's actually also a linear data structure, you can see here. And it's a dynamic data structure, meaning you can be able to increase the size. Now, this is true depending on how you implement the data structure. As you're going to see, we can implement the data structure either using an array or using a linked list. But for Python, in Python, really, instead of using an array, we are going to be using a list, which is also dynamic. So really, let's move forward and see how this pans out. Now, this is another analogy of the last in, first out principle. So if you're a fan of bracelets, like this lady here, you see, for you to be able to remove this black and white bracelet, you must begin with this one. So you have to remove that one, then the black and white, and then this one, then this one. So the last one for you to put in is the first one for you to really put out. And this particular animation in this slide is simply going to show us that So for example, if you have the value A, it's going to be stored in the stack just like that. Then maybe you also have a value B, which is going to be stored in the stack like that. Then maybe C, then maybe D. And then what if the stack is full? So the stack can have a fixed size. For example, when you're implementing it using an array, but it can be dynamic if you're implementing it using a linked list. So what if it's full and you still have a value E that you want to store in the stack? What do you think will happen? So if you guessed it right, then that is exactly what will happen. So the stack is full, so no more space, and therefore this is going to result into really an error. Again, if we want to remove elements from a stack, we need to begin from the top. So there is always an arrow which acts as a pointer to the element on the top, just that element. So if we wanted to remove D from the stack, we are simply going to refer to the arrow, remove it, then decrease the value of the arrow, which is now going to point to the next element, C. And then if we remove that, again, the arrow moves down to the next element like that, then to the last element. And once we are done, then the arrow is also decremented to a negative number. So this idea of adding things to the stack and removing them have a special name in stacks. So adding things to the stack is called a push operation, and removing things from the stack is called a pop operation. In a short while, we are going to see other stack operation. So this is a good challenge for you. Feel free to pause if the timer is moving too fast for you, but give it a try. Okay, so let me just mention something here. So of course, we've said that it is lethal for the stack data structure. In our next topic, we're going to look at the queue, and the queue, for example, uses the first in, first out data structure. And the queue is just like any other queue you've ever made. For example, when you're buying food in the pavilion. So whoever comes first is served first. So first in, first out. But for example, if you have a stack of books, for you to access a book that is on a lower place, you have to remove the ones that are upper. So that is last in, first out. Okay, so these are the basic operations of the stack. I've already explained the push and the pop. The other ones that we are going to look at is pick. The pick operation returns the element that is at the top of the stack without removing it. So we just want to check what is the value at the top of the stack. Then the empty operation checks if the stack is empty. So again, give this a try. Okay, congratulations. I know you got it right. Okay, so as I mentioned earlier, you can implement a stack using an array or using a linked list. Each of the methods have their advantages and disadvantages, and for that you need to, from this you need to understand when and not when to use each of the methods. So with arrays, they are easier to implement. As you know, linked lists, it's a bit difficult to implement a linked list, but an array or a list in Python, very easy to implement. It's also efficient because you can access elements just using the index of that particular element on the top of the array. But for linked lists, sometimes we know that that is not possible. We also have better cache locality. You remember when we were learning about arrays, we say that this is an advantage because items are stored next to each other. So we don't have to move the memory head far away to get to the next item. But for linked lists, items are stored at random memory locations. So that does not provide a very favorable cache locality. It also requires less memory overhead compared to linked lists, because you know that linked lists need also to store the reference of the next node, which consumes some amount of memory. The problem with arrays is limited capacity because it's going to have a fixed size, and you know that in case we need to resize the array, that becomes a very costly operation in terms of time and space complexity. Also, insertions and deletions at any other particular position is less efficient, but this really is not for a stack. So forgive me for having that there. Then, if the array needs to be resized frequently, it can lead also to performance degradation. As I've already mentioned, when you need to resize an array, it becomes a very expensive operation. Then the advantages of a linked list, number one is the dynamic size. So you don't need to know the size of the stack beforehand because it can grow to as much as it wants to. It's also efficient when it comes to insertion and deletion at both ends of the list, either the head or the tail, because we can always know the tail and the head, and we can do the insertion and deletion in an O of 1 time complexity. There's also no need for resizing, as we said, unlike arrays. So for the disadvantages of linked lists, they require additional memory. We've already mentioned that for storing the next pointer. Also accessing elements by index is less efficient. No, not really. This is also not supposed to be here. And then traversing the list to access elements can be slower than arrays due to the cache inefficiency. So that's just the same explanation I gave for this. That because elements are stored at different memory locations in linked lists, so it's slower to access them. But because the elements are stored in contiguous memory location with arrays, then it's faster to access them. Okay. So these are some of the real-world applications of the stack data structure. We already learned about this when we were learning about recursion. So as you know, every function call, if a function is calling another function, or we have a function calling itself, every other function call will be stored in a stack. So here, if function 1 calls function 2, then function 1 is stored in the stack. 2 calls 3, 2 stored also in the stack. Then 3 calls 4, 4 also, 3 also stored in the stack. Then 4 will print 4, then it will come back to executing 3, 3 will print 3, then this is going to be popped out of the stack, removed out of the stack. Then 2 is going to be executed, which is going to print out that. And then when you get to the end of that function, 2 is also popped out of the stack. Then 1 is going to be executed like that, and it's going to print 1. So this particular program, if you can remember it, you're simply going to print 4, then 3, then 2, then 1. So that is one of the uses of the stack memory for storing the temporary results of function calls that either call other functions or call themselves. Then the stack is also used to manage the browser memory. So here, when you have the previous and the next button, if you visited multiple web addresses in the same tab, so as you're moving from one a website to another, they're simply being added on the stack. And when you click back, then it's popped out of the stack and you're able to access it. So that is how that happens. It's also used for balancing of symbols. Of course, this is Python, and Python does not have many symbols as such, unlike C and C++ and even Java. So here in Python, one of the common symbols we have is the round brackets. So every opening round bracket must be closed. So we have an opening and a closing one. So what happens is when the first round bracket is encountered, it is added into a stack. So let me just see. So in case we have the stack there, so we encounter the first one, then we add it to the stack. So just imagine that we have it on the stack like that. So when we find the next one, the closing one, we simply remove this from the stack. We remove it. So we just remove it from the stack. So anytime we have just one item in the stack, it means that we do not have the closing one. And like in this example on line 46, the compiler is now going to know that there is an error because we have an opening round bracket that has not been closed. So that is how that works really. So that is what we call balancing of symbols, and really your debugger is going to use that to detect any symbols that have not been closed, that does not have a matching closing symbol. It's also used for string reversal, and this is one of the challenges that you can actually get when you go for your first technical interview as a junior developer in any software development company. So if you want to do string reversal, one of the quickest way to do it is to traverse that particular array, because a string is just an array, as you add every single item in a stack. Then in order to be able to get the reverse, you then just pop every item as you store them, for example, in a variable. And that is how you achieve string traversal. So please remember to always practice string traversal, string reversal using a stack before you go for any software development technical interview. It's also used to do the undo and redo. Please read more on this when you get time. And lastly, it's also used for backtracking algorithms. Like, for example, if you're playing a maze game in a computer and you hit a dead end, for you to be able to go back, actually that data is, every move you make is actually saved in a stack. And for you to go back, when you're going back to point B, it's popped out of the stack. Then you can be able to go back to point C, etc, etc. But as we are going to see when we learn about the graph and also the tree data structure, okay, let me use red for this. Okay, so we are going to learn about DFS, depth first search. This is an example of a tree data structure. And for depth first search, we normally strive to access, sorry, we have to visit the very last node. So that is why it's called depth. So you come from A and then B and then E, then maybe print E. Then you're going to come back to B. Then again, we explore the depth that is on the left side of B. And my mouse is misbehaving. We come like that. Then after that, we go back to A. Then we explore whatever is on the left of A. We explore the depth of what is on C. Sorry, not that direction. Like this. Like this. Then we go back like this. Then we go back to visit whatever is on the right, actually. Then like this. Then we print that. Then we go back to A. So that is what we call depth first search. So as we are visiting these nodes, we normally add them to a stack. Please remember this, because you'll need it. You'll need it in very few topics to come. So we normally add every node we visit. We have to add it on the stack. And anytime we print a node, for example, here we'll start by printing E, we pop it out of the stack. Then go back to whatever was just added before E, we find it's B, then we look, does it have any child to the right? If it does, we put it on the stack. Then we check, does F have any child? It does not. Then we print F. Then we remove it from the stack. Of course, we are going to go back to B. Like that, like that. So that is how we really implement DFS. So you must use a stack to implement depth first search algorithm. Okay, so give this a try. Okay. So these are the time complexities when you're using an array, but in Python, really, we're going to be using lists. So for creating a stack, the time complexity really is O of 1. Space complexity, I can call it O of 1, but if you're having many items, of course, it's going to be O of n. But it's just, if it's just declaring an empty stack, then it's O of 1. Okay. Then we have the push operation. On average case, it's going to be O of 1 for an array. So this is when we are saying that you're just adding an item to an array, and the array still has some space in it. Otherwise, if you try to add an item to an array and we don't have space in it, you know what will happen? A very expensive operation. The system is simply going to look for some other place where we have contiguous memory, where it can be able to create recreate that particular array with a bigger space. So that's why we are saying that on worst case, a push operation will have an O of n time complexity. Popping is just removing what is on top of the stack. So O of 1, picking, just looking at what is on top of the stack. So O of 1 operation. And to also check if a stack is empty, it's also an O of 1 operation. This is not very different. This is not very different from when we are using a linked list. My challenge to you is, I'm not sure. Can you just confirm whether this, maybe you can put it in the comment, confirm whether this is correct, or did I forget to remove this? I think I actually forgot to remove this. This is not supposed to be there. This is not supposed to be there. So for linked lists, all the operations, including the push operation, by the way, they're just of one operations for a stack. So you can see a stack is a data structure that is quite efficient. Great. Another quiz for you to attempt. Okay. Wonderful. So we have defined a stack data structure as one that is linear and follows the last in, first out principle. We've also seen the properties of a stack, including the fact that it can be dynamic or fixed size. And we've also looked at the stack operations, including just the basic ones, including the push, pop, pick, and is empty operation. And lastly, in this lecture, we looked at the time complexities, just noting especially the difference between the time complexities when you're using an array to implement the stack vis-a-vis when you're using a linked list. And we've seen that especially for a linked list, which is one of its greatest advantage, is the fact that all operations really are basic operations are actually an of one time complexity operation. So thank you so much for sticking to the end. In the next video, we are going now to implement the stack in Python using lists. So those operations. So very exciting practical experience. So see you in the next video. Thank you. Bye-bye for now.